Good morning, students. This is the session 15 from the playlist of electric charges and fields, and today we will be deriving the equation for the electric field at a point due to an infinitely long thin charged wire. So I have drawn here one figure in which I have shown this as a thin infinitely long charged wire which is having a linear uniform charge density of lambda. This wire is assumed to be present in free space, and I have to find the intensity of electric field at this point P, which is at a distance of r from this charged wire. So, in order to find the electric field at this point P, I will be using the Gauss law. Now, as per the Gauss law, the electric flux which is passing through a closed surface is given by Q upon epsilon naught, where Q is the total amount of charge which is enclosed by that closed surface. So here, what we have to find, in order to find the value of this flux using the Gauss law, I will have to create a one Gaussian surface, as I have already made it here. You can see it here. This is the Gaussian surface which is shown with the help of these dotted line, and this is a Gaussian surface which is cylindrical in shape. So this is the Gaussian surface which is cylindrical in shape, and this Gaussian surface has been constructed in such a way that this point P is enclosed by this Gaussian surface. So now, as per the Gauss law, the flux which is passing through this Gaussian surface will be equal to Q divided by epsilon naught, where Q is the total amount of charge which is enclosed by this Gaussian surface. Now here I have assumed the length of this cylindrical Gaussian surface as L. I have already indicated here on this board, and and here the linear uniform charge density is equal to lambda. So if the linear charge density is lambda, then lambda is equal to Q upon L. L is what? This is the length of the conductor which is inside this Gaussian surface. This is this cylindrical Gaussian surface as shown by this dotted line. So the length of the conductor which will be inside this Gaussian surface will also be equal to L. So if it is so, and if lambda is the linear charge density, then Q will be equal to, that is, the total amount of charge which will be enclosed by this Gaussian surface. This will be equal to lambda L. Or we can simply say that the flux through this Gaussian surface will be equal to, that is, Q upon epsilon naught, so this will be equal to lambda L upon epsilon naught. So this is the first equation which I have got. So the flux through this Gaussian surface is equal to lambda L divided by epsilon naught. This is the first equation. Now there is one more equation for calculating the electric flux through a surface which is placed in an external field. That is, I am just drawing one figure here. This figure will not be this figure which I am drawing here will not be symmetrical, because I am just trying to explain you that the value of this electric field through this surface which is placed in an external electric field is given by Es cos theta, Now theta is what here? Theta is the angle between the direction of electric field, say E, and the normal to the surface. And here S is the surface area of this surface. So this is the surface which is placed in an external field. So the flux which is passing through this surface, which is placed in an external field of magnitude E, then phi will be equal to Es cos theta, and theta is the angle between the direction of this electric field E and the normal to the surface. Now the normal to this surface, in this case we see here, this will be something like this. So this is the angle theta. If this surface was lying perpendicular to this this electric field, then the normal to this surface would have been along this direction of this electric field. So in that case, theta will be equal to 0. But now here this surface is inclined, is not perpendicular to the direction of this electric field. It is slightly tilted, and because of that, the direction between this the angle between the direction of this electric field and the normal to the surface will be like this. This is the normal to the surface, which I have not been, means the normal to the surface will be something like this, okay, like this, and the direction of the electric field is like this. So the angle between this normal to the surface, which I am writing here as n, and the direction of this electric field, this will be this is equal to theta here. So here in this case I will be using this formula in this case also. So here you can see that this is a uniformly charged thin wire. So, and this is a positively charged wire. So the direction of this electric field will be directed radially outward. Okay, so I have already drawn the direction of this electric field because of this positively charged thin wire. Now, let us consider, now this cylindrical Gaussian surface can be considered to be made of three surfaces, that is A, B and C. This is the you can say the top surface of this cylinder, this is the bottom surface of this cylinder, and this is the curved surface. Now, flux is equal to Es cos theta. So the flux through this surface A will be 0, because here the normal to this surface is pointing in the upward direction. So the angle between the direction of the field, that is this E, and this normal to the surface A is 90 degrees. So the flux through the surface A is equal to 0. Similarly, the flux through the surface C will also be 0, because the normal to the angle between the normal to this surface C and the direction of the electric field is also 90 degree. So cos 90 is equal to 0. So this is equal to 0. Now we have to simply find the flux through this curved surface B. Now here this is a curved surface. So the normal to this curved surface will be like this, and this will be along the direction of the electric field. So here the value of theta will be 0. So the flux to this curved surface will be equal to ES. S is the surface area of this curved surface, which will be equal to 2 pi RL, where R is the radius of this Gaussian cylinder. And because now this point P is also enclosed by this cylindrical Gaussian surface, so this point P is also situated at a distance of R from this charged wire. So and this R is also the radius of this cylindrical Gaussian surface. So phi, that is the flux to this curved surface, will be equal to E into 2 pi RL into cos 0, which is equal to 1, and this is equal to lambda L upon epsilon naught from this equation 1. So we can say that E 2 pi r L is equal to lambda L upon epsilon naught. From here L and L will get cancelled out. So we can say that the electrical field at this point P, which is at a distance r from this infinitely long charged wire, this will be equal to lambda divided by 2 pi r epsilon naught. So this is the intensity of electrical field at any point P, which is situated at a distance r from that infinitely long charged wire, and this is equal to lambda divided by 2 pi r epsilon naught. So E is basically, from here you can see that if the linear charge density increases, then the value of this E will increase, and the value of E is inversely proportional to the distance of the point from this charged wire. So if R increases, then the value of E will decrease. So thank you very much for joining this session. In the next session, I will be coming up with another derivation in which I will be taking the an infinite. I will be taking this rectangular sheet of infinite length, and we will be deriving the value of this electric field due to that infinitely long this rectangular sheet having a uniform surface charge density. So thank you very much. Till then, have a nice day. Bye.